Hi guys, today we're going to take a look at page 12 at the bottom and page 13. Let's see, we're going to look at 14 as well. Yeah, we'll take a look at pages 12, 13, and 14 of the classwork packet. Alright, 12, 13, and 14 of the classwork packet. Sounds like a lot, but it's really not. Now, first things first, there's a special property that applies to tangent lines, and a tangent line intersects a circle at exactly one point called the point of tangency. A line is tangent to a circle if and only if it is perpendicular to a radius drawn to the point of tangency. That's a fancy way of saying this, all right? Here's a circle, right? Here is a tangent line. Here's my point of tangency. And all it's saying is that if I were to draw a radius from here to here, it would end up giving me a right angle. Now, for our purposes right here, all we really need to know is this. If I, for whatever reason, were to extend a line segment from the center right here over here to the tangent line, what kind of triangle have I created? I've created a right triangle, and in this case, a right triangle is only a right triangle if what of my favorite theorems holds. Oh my gosh, could it be? Yes, it is, the Pythagorean theorem. So all we really have to do here to determine yes or no, is it tangent, is to look at whether the Pythagorean theorem holds true. Let's take a look together at example 1 so you can see how this works. Okay? So number 1, they've given us what looks to be like a nasty problem, but in reality it's not, all right? Here's my radius of 8, there's 15, and here's 17. And all they're really asking us to do is say, does the Pythagorean theorem work? So here's the question we have to ask ourselves. Does 8 squared plus 15 squared equal 17 squared? And I'm going to put a question mark right here so we can say we're not quite sure yet, but we're testing to see if it actually works, right? So let's see. 64 plus 225, does that equal 289? Let's check. 289, does that equal 289? Yes. So because the Pythagorean theorem holds, we would say, yes, it works. In other words, yes, that line right here is tangent because the Pythagorean theorem works, and that means that I have a right triangle. Okay? Now, another way that they could test this, right, is by using an algebra problem. So let's take a look at page 13. Once again, what page number? Page 13. And let's take a look at question number 4, shall we? All right, now number 4 is a little tiny bit tricky, not too much, all right, but it does require you to use a little bit of logic here, all right? First things first, if this is 11, right, what's this right here? Also 11, because all radii are congruent, and therefore this is 18. Now, once again, what theorem do I have to use in order to check to see if it is a tangent? Well, I'm just going to use Pythagorean theorem. The only difference in this case is notice this right here is a leg, so I'm going to have to say x squared plus 11 squared equals 18 squared. Why is it like that? Why is it not 11 squared plus 18 squared? Well, because 18 would be the hypotenuse because it would be across from the right angle. So let's check. So x squared, right, plus 121 equals 324. Subtract 121 from both sides, so I get 203. Let me write this a little bigger for you. So x squared equals rad 203. Sorry about that. X squared equals 203. Getting ahead of myself there. So x is rad 203. In your homework, I'll probably ask you to actually round that to the nearest tenth. So you would just pull out your handy dandy calculator for once and hit the square root key, bada bing, bada boom, and you would be done. Okay? Now, that's one type of problem that involves tangents. Another type of problem is what you see at the bottom of page 13. These are what I call the ice cream cone problems. You see how each one looks kind of like an ice cream cone? I mean, most ice cream cones are not actually going to have that big a scoop of ice cream relative to the cone part, but, you know, you get the idea, right? So basically, if I have two tangents, right, and they have a common they intersect, right? They have a common intersection point outside the circle. They're going to be congruent to each other. So when you see a problem like number 10 or number 11, all you really got to do is set them equal to each other. So let's take a look at one example. Let's take a look at question number 10. Once again, what number are we looking at? We're looking at question number 10. So number 10, blah, blah, blah. Here's a circle, here's a tangent, and oh my gosh, look, they intersect. Therefore, they are congruent to each other. So if you guys want to think about this visually, the ice cream cone problem just means that they're congruent to each other. So I'm going to say 8x minus 19 equals 5x plus 23. Let's subtract 5x from both sides and add 19 to both sides. And I got 3x equals 42, and therefore x equals 14. All right? Now just be careful. In this particular example, all I asked you to do is solve for x, right? However, what if on the homework I would ask you to actually find like how long this was? Then you might have to plug x back in, all right? So just be prepared for that. I may ask you to do that. Make sure you read the directions carefully, okay? All right, next up, we're going to take a look at page number 14. This is an application of the ice cream cone problem, right? Basically, what you're going to do is you're going to be creating multiple ice cream cone problems in one figure. And let's see how that's going to work, okay? So let's take a look at question number 13. Once again, what number? Number 13. So, question number 13 looks like this. Here's a circle. And then, oh my god, what the heck is this? They've drawn like this weird triangular thing around it, haven't they? Okay. I know that's not exactly perfect, alright? I apologize if it's not the best, but, you know, like I said, we just kind of have to deal with it sometimes, right? Okay. So the basic idea here is this. If I have two tangents that are intersecting outside the circle, they're congruent to each other. So basically, if this is 9.5, what's this? Also 9.5. If this is 16, what's this? Also 16. If this is 11, what's this? Also 11. And so, when they ask us to go around and find the perimeter, what does perimeter mean, guys? Perimeter just means go around and add up all the sides. So let's take a look. 11, that's 22. 16 is 16, that's 32. 9.5, 9.5, that would be 19. So let's do a little bit of addition here. 3, 6, and so I would get that they add up to 73. All right? So again, what do we need to take away from this? Two things. First, if they ask you, is the line tangent, your automatic first thought is Pythagorean theorem. If it works, yes, hooray. If it doesn't work, oops, sorry, no. Big idea number 2. If I have two tangents that are intersecting outside the circle, right? They meet outside the circle, they're going to be congruent to each other. And so I can, in algebraic cases, set them equal to each other. Or if I get this weird perimeter problem, I just have to kind of fill it in. And then I'm going to add, because that's what perimeter means, to add up all the sides together.